Hi Year 10, today we're looking at relative frequency. So your 6 questions for the starter are up on the screen. Pause the video, have a go at all 6 of these, and when you've finished, unpause the video to mark them. Okay, you should have done all 6 of these now, so with your red pens, can you please tick them if they're right and change them if they're wrong. Remember, feel free to pause the video if you need more time to mark, but we're going to move on. So this one's slightly different because this kind of experiment is great in a classroom during a lesson. At home it's slightly more difficult, but you can still have a go at this in order to illustrate relative frequency in real life if you'd like to. So what you're going to do is grab a coin, any kind of coin will do, flip it and record the number of times you flip a head. Now you're going to do this 10 times, that's our total number of trials, and then each time you hit a landmark, such as 1 trial, 5 trials and 10 trials, record the total number of heads you flipped up until this point. After you've done that, you're going to calculate the experimental probability, which is found by dividing the total number of heads you flipped over the total times you flipped the coin, and that's going to give us our probability here. So if you want to have a go at this, pause the video now, grab a coin and start doing the experiment. If you didn't have a go at this and you want to just see what the experiment results will look like, we're going to do it theoretically in our heads. So let's say I flip a coin now, it's either going to land on heads or it's not. So let's say it lands on heads this time, we've been successful. We have 1 heads out of 1 total trials. So if I'm finding the experimental probability, I have a probability of 1 over 1, that's my number of heads over my total trials, which gives me a probability of 1. Now we know that this isn't an accurate probability because this means that the event of flipping a head is a certain event, but we know that's not true for coins, it's actually 50-50, so this is just reliant upon the data I have rather than what I know about coins. Let's say I flipped my coin again and out of 5 trials I actually got 4 lots of heads. Now if I'm rewriting this as a fraction, I get 4 over 5 as my new experimental probability, which is a probability of 0.8. Now I can see that even though this still isn't accurate to my theoretical probability, it's getting closer to what I expect. So it's no longer certain, but it's still saying that getting ahead is likely. Let's say now that I flip it again, and out of 10 trials I get 6 heads. I have a new experimental probability of 6 over 10, which is 0.6. So I now have a probability that is getting closer to my actual probability that I would expect. So the question is, how did the calculated value of the probability change as the number of trials increased? Now we saw that it got closer and closer to what you'd expect the probability to be for flipping a coin. And the reason for this, even though it seems quite intuitive to you, is down to a law discovered not that long ago. So the law of large numbers was first published in 1713 by a man named Jacob Bernoulli. So we use it a lot in any kind of probability and statistics. It's the reason why if we do science experiments or any other experiment, we have to repeat it large amounts of times to check how valid, accurate and reliable our data is. And it states that as the number of trials increase, the experimental probability will get closer and closer to the theoretical probability. So the more times we do it, the more times our probability calculated will be close to the probability we expect. So what I want you to do on your piece of paper is to split the paper in half and head each half of it with theoretical probability and experimental probability, and we're going to look at the fundamental differences between these two types of probability. So theoretical probability is the probability you expect. It's found by dividing the number of successes, or what you deem to be a success, over the total number of outcomes. So for example, we said that for flipping a coin, let's say we want a heads, the number of successes, well, we can only get 1 success, which is flipping a head. The total number of outcomes is either heads or tails, so there are 2 outcomes, so therefore our theoretical probability is a half. Now our theoretical probability isn't based on any kind of data, so we don't need to do any trials or any kind of experiments. It isn't based on trials or data, and therefore this kind of probability doesn't change. It doesn't matter what we do, our theoretical probability will stay the same. On the other hand, experimental probability is probability we've calculated. So we saw before that it entirely relies upon data we've used, and it's found by dividing the number of successes, so how many times we flipped ahead, over the total number of trials, so how many times we've actually tried flipping the coin. So this can be any kind of probability. We know it's going to get closer and closer to the theoretical probability the more times we do it, but it can be any probability between 0 and 1 for an experimental probability, depending on how many trials we do. So this is based on data. And the key thing is that the experimental probability does change depending on how many times we do the trial. So it's not always going to stay the same depending on what we do. So the next slide is going to summarize the key differences. This is just our own notes that we're going to use. If you miss anything, you see something on the next slide that you want to add, then feel free to. But the next slide is just summarizing what we've covered so far in the previous 5 minutes. So relative frequency, which is the name of this lesson, is another name for our experimental probability, and it's used when probability is being estimated from the outcomes of an experiment or trial. Theoretical probability isn't always used, so sometimes we have to rely on experimental probability. For example, if we don't know the probability of an experiment, we would rely entirely on our law of large numbers telling us what our theoretical probability is going to be roughly. So relative frequency or experimental probability is calculated from the number of times an event happens divided by the total number of trials in an actual experiment. So that's given by this formula here, the one we looked at before. We always get a value between 0 and 1, so it's like any kind of probability, and we can rewrite it as a fraction, a decimal, or a percentage. So if you get a probability that's either less than 0 or greater than 1, you know you've gone wrong somewhere, because probability cannot be any kind of value that is not between these. Finally, our law of large numbers, the accuracy of the relative frequency is always improved by increasing the number of trials we do. Okay, so let's put our experimental probability into action. Let's say a coin is flipped 50 times and we want to find the relative frequency of heads if heads came up 27 times. So what we're saying is that the number of total trials is 50 and the number of successes is 27. So using our formula, which is number of successes over the total number of trials, this gives us our experimental probability. Now you don't need to turn this into a decimal, a fraction is completely fine, so I'm just going to leave it in this form here. Okay, what you're going to do is pause the video, have a go at the second one where we're trying to find the relative frequency of tails. As a heads up, I know the answer is wrong on this because I had just had a look, but I will correct it as soon as you unpause the video. Okay, so your real answer should not be 37 and 50, that's a different kind of probability from a different question. But our probability should be 13 over 50 because that is our number of successes over our total number of trials. And there's no need to turn this into a decimal. 13 over 50 is a perfectly acceptable answer.